So, good morning, everyone, and welcome to our Big Data course today. Today, we're having a guest lecture, and I'm very happy that Ramón Medrano is giving the guest lecture. Ramón is a senior staff software engineer at Google. He's an expert in site reliability engineering, and I met Ramón the first time like 12 or 13 years ago when we both worked at CERN at a much earlier stage in our career. I then stayed at CERN a little longer, and Ramón left earlier in order to join Google. And in parallel to your work at Google, where you've been now for more than 10 years, you also did your PhD part-time with the University of Oviedo. So you all see Ramón keeps working very hard, and I'm very happy that you're here today for your guest lecture.
I'm very happy to. Thanks for the introduction. So I'm going to share my screen. I prepared some slides, but beware that I have many of them, and I don't think we're going to cover all of them. The goal is not to cover slides. I don't care about the slides, but to learn what is. So what I want to show you is what is production, basically. That is a place that is very weird and very complicated. Right, so I don't know if you are being able to see my slides.
Your slides are perfectly fine, and I turned off my camera just that the floor is all yours. So please go ahead.
Excellent. So we are mostly set. Then I'm happy that it only took like 5 minutes. Sorry. So what I was saying is like the goal of this lesson is not to cover slides, because slides are just a material. I'm gonna share it with you, the material, my email, everything. So if you have questions, like that's, knock yourself out. So what I want to tell you is what is going or how it looks like to be in production, right? So I remember when I was studying, or when I was like doing my experiments, my practice, my labs, right? That's a way to learn the basics, the fundamentals. But then when you go to production, things are hairy and uglier, right? But it's nice. Like don't get me wrong. Like production is good, right? So anytime that you have a questions, just go for it, raise your hand, like interrupt me, whatever you want. There is going to be probably time at the end for questions as well if you prefer. Then I'm going to show you what I learned from the experience of running transactional systems, right? So transactional systems in the sense of like a classic big data systems, that they are like, transaction processing, online, like OLAP systems, like analysis, batch pipelines, all that stuff. So for your context, we have, my team is the one that runs the authentication and authorization services at Google. So we have tens of billions of accounts. We have like hundreds of millions of queries per second to our service, all of the services in the company and products that use our infrastructure. So in a sense, it's like big data, but is used not only for our product, like sign in, but for basically everything that you can imagine. Like, for example, Gmail, sending an email, will need to consult what is your account and all that stuff, right? I'm gonna as well do mirror during the presentation what happens when you do deploy AI to this system. So AI is a thing that you might have realized that is coming up, right? And it's quite different from the perspective of production, right? For example, when you have a database that is just doing like a key value store, and you retrieve and you search for some values in your database, that's in a sense like binary. So either succeeds or it doesn't succeed, and so on. Systems that they have like an AI model in the core, right? They provide answers that they have a variety different of quality. You are going to have to think about safety. You are going to have to think about like, for example, scaling these systems have is quite different. So I'm going to just try to interleave different comments on the way. So let's just go get started. So I put the title Site Reliability Engineering because I really did not know exactly how to call it. That's because that's what I do. You can call it production or like big data in production. You choose, right? So first of all, what is SRE and why? This is just to give you like a minute slide of context of where I'm coming from in the sense of like observing or understanding systems. Right? That's my bias in a sense, right? So one thing that you need to understand is like software engineering, right? Is not writing software from the scratch where the cost or the value is. Like releasing the first version is the easy part, right? So having version 1.0, just shipping it, and then you are done. That's not the thing, like, because more than half of the cost of maintaining or the cost that goes into the software is going to be the maintenance and after you're done, because you're going to need to release new features, but you're going to need to patch, like, security vulnerabilities. You're going to need to upgrade your libraries. You're going to need to resolve, like, incidents that they happen while the software is running, and so on, right? So I think that where the cost of software is after it's done, in a sense, right? So SRE means site reliability engineering. Basically, like, that was not a very, like, clever kind of meaning, right? But basically, reliability is part of engineering that we, like, focus in dependability. So what we want for reliable systems is, in a nutshell, systems that they do what we tell them to do when we tell them to do it. Right. So that means there's a lot to unpack to have that. So you are going to need to have systems that they are available. So when you want them to do something, they are there for you, right? And then they have to be correct. So when you have an operation into your system, it needs to be successful, but needs to do what it's supposed to do. For example, in the authentication world, when you want to authenticate a user and provide them with a credential, right? You want the system to be available, but as well to authenticate the user that is requesting the credential, and with the correct, set of challenges, like a password, second factor, whatever it is, right? If that is not true at any point in time, your authentication system is basically BS, in a sense, right? Engineering, I think everyone knows what engineering is in there, but I think, like, it's a nice reminder, because what we do is, engineers is applying science. So we have mathematicals, empirical evidence, economic science, social sciences, anything that is scientific and come after the scientific method, right? We just turn that into applications. That's what we do in engineering. And that can be from building machines to building machine learning models to, like, build observability for a system, right? And then a site, well, that's a site, like a web. Right? So what does mean being a software engineer in SRE at Google? Means that you are a software engineer, right? But your role or your features for your product is reliability. And that meaning that the service is always available and is correct for the user. So I write code in the core of services, Gmail, or, like authentication stuff. But I'm not gonna, like, be focusing into, like, how the visuals look like and so on, right? That's for user experience researchers, but I'm going to be focusing to making sure that our retries, for example, they are right, the schema of our database is optimal, I have the right indexes where I need them, so the system behaves, like, correctly for everyone that is going to be using it, right? So we do engineering solutions, basically focusing on reliability, right? We are not different job role in a sense. Well, it's called, like, SRE, but it's like we are software engineers at the end, and we are focusing into big distributed systems, right? And one thing that we do is design these big distributed systems. So when you think about big data, right, you're going to have to think about the whole change of a system that processes a lot of data. So it's not only the running pipelines that they are going to run summaries or whatever, right? But it's going to be as well, like, the ingestion of the data integrity. Is going to be, like, replications of the data is available with low latency across the world. Is going to be things like a consensus in distributed systems. So when you want to do, like, a modification of your data, that's consistent. Is going to be disaster recovery, etc., 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 right? So this is all the things that we do. Like, we are going to be doing reactive things in the sense of, like, production is going to break at some point, right? For example, I'm pretty sure that we use, I don't know how many machines, I don't know, hundreds, thousands, let's just say, just for the sake of saying, but I know that many of them, they are broken at the moment. Some of them are rebooting for a new kernel, like some of the disks, they are broken because they just, they break all the time, right? But I have designed my system to tolerate all these faults, right? So that's something that is proactive, right? So we think about, like, what is the problem that we need to solve, and we're going to need to analyze all the failure domains that they can go into my distributed system, so it will be resilient of all these errors, right? And then there are things that they are reactive. At some point, you're going to have an outage, right? Because you're going to have it. Like, that's it's not if, but it's like when, right? So you're going to need to be prepared to have a response to the outage that is as quick as possible, in the sense of like, the medium time to repair is the shortest as possible, so your users can come back to use your service as fast as possible, right? And then there are many other things that enable that. For example, things that they are very interesting, they're capacity planning and provision. So when you use the cloud, there is no capacity planning to do. In principle, it's unlimited. But when you are the cloud, right, you need to do some capacity planning. For example, you need to build buildings, right? So when you operate at a scale like Google or Microsoft or AWS operate, right, you're going to need to do things like it's not only commission machines, right? But as well, there is a point that you are going to need to make a building for a new data center. That's going to take a few years, and you are going to need to buy land, and you are going to need to, work with the local utilities to get you like so many megawatts in place, and you're going to need to have failovers and so on and so forth, right? And this is all the stuff that we do. As you see, this is software engineering, but it's like a very multifaceted kind of approach, right? And this is something that you are going to find whenever you move from like small projects that you are prototyping and so on and into production, is that you're going to discover that even if it's like a small to medium application, very quickly, there are many problems and many things that you're going to need to figure out in the way. So, any questions so far? No? Good. If you have questions, just remember that there's no stupid question. What is the tenet that so many people like that they are doing DevOps? For example, when I use DevOps, production engineering, SRE, and so on during this talk, they are using them interchangeably. So there is like nuances of the different roles and how they're implemented in different companies and places. But for the sake of the discussion, let's just say it's the same, right? There is one way for making systems very reliable, right? That is like, is the definite way to make a system very reliable is not to touch them. So you don't change it anymore, right? So you don't do new features, you don't do new libraries, you don't add like AI to it, you don't do like new interface, you don't do nothing, right? It's likely not going to fail. Like the infrastructure when you build it can fail, but if you don't touch it, it's going to be fine, right? You're going to be out of the market relatively soon if you do that, right? So it's going to be available, but no one's going to use it because some competitors are going to come up, some new systems and so on. So you're going to want to change your system, and you're going to want to change it really fast, right? This is the maximum change velocity. So you want to change your system as frequently as possible, right? The problem is like about 70% of the outages that we see at Google and outside, they come, they are triggered due to changes. So you push a new binary into production, you push a new configuration file, you push a new schema to your database, right? And those trigger outages from time to time. For example, one outage that we had like a few years ago, it was the following. There was a change in an schema of the database that it was like, trivial in a sense, like we are going to change the default of a field, right? And then there was a batch job that they was running over this database, like computing some stuff. When the change was triggering into the database, this batch job was modifying the database in some unforeseen consequences, right? And it took down the whole authentication service of Google, right? So even smaller changes can have like outsized impact into your service, right, or into your product. So then you're going to need to choose as well how much reliability you want in your service, right? And when you talk to some people, they're going to say like, well, my service is really important. I'm going to have 100%. Like, it cannot fail, right? That's probably wrong for one very simple reason. The more reliability you want to target, the more complex your system is going to be, because the more faults it will need to tolerate, right? That complication is going to like self-fulfill the prophecy of like, the more complex the system is, the more outages it can trigger, because complexity tends to make systems less reliable, right? So like you're going to have to choose how important your service is for your business, your company, your like research project, whatever, what you're doing. Typically 100% is not the right thing in there, right? So you're going to need to tolerate some errors in your service. That's a fact of life, right? Services are going to fail at some point, right? The question is like how much, right? And if a small failure that you're going to have, a small outages, is like is just fine for what you're doing. And depending of what you're doing, right, you are going to be able to tolerate more failures or less failures, and that's okay, right? We have services that they are aiming for like 6.5 nines, and others that they are aiming for like 90% availability. I will cover that slightly later, right? So each of the services, they have their purpose, and the balance of like reliability and risk that you can take is just different, and that's fine. So now let's go into some matters. So what is the production environment we have at Google internally? This is an introduction. You are going to find many, many resources outside, right? So the first thing that we have is like, for us, things and services, they are cattle and not pets. I know that sounds like, like very like, oh, like a fancy thing for putting in Twitter and so on, but that's true, right? In the sense of like, when you are managing services as a pet, you're going to have things that they have a name. For example, you're going to have your free servers, right? And then you're going to put names like Orion, Andromeda, whatever in your machines, and then you're going to deploy things like very bespoke, right? And you're going to have to like, things that they're very like customized for what you do. That's totally okay when you operate in a scale that allows you to do that. It's relatively expensive, right? And the things like the cost to the size of the fleet is non-linear. So when you go from 3 machines to 10, right, you are going to find yourself like spending like all your time managing these 10 machines, right? If you use the same approach and you have 100,000 machines, you're going to need to hire like a whole legion of people to keep doing that. So this is why we do cattle. And cattle, basically, how you do that is like you stop caring about the machines and you care about the automation around the service, right? So you start applying software engineering to your problem. In this case, managing large amount of machines, which is a big data problem by itself, right? So data centers. Production is run in data centers. So when you go to your cloud and you ask for some GPUs for doing your training or your models, and then you do a RAG and you want to put a nice front end, and then you like create like a search engine over documents or whatever is what you are doing, right? You're going to run it in a data center at the end of the day. Data centers, so are weird place. They are like a big building, it's full of machines, it's a very noisy place, it's a very cold place, right? And it's very hard to find things. So when you go through a data center, there is just a place that is full of like racks and racks and racks and racks of machines, right? And machines that they are all basically the same thing, right? So why data centers? Data centers are just very efficient. So you can have a lot of machines sharing like infrastructure, like for example, network connectivity. You're going to have like all the cooling machinery is going to be the same for all the building. You are going to have like personnel that is trained in one data center and they can manage all of them because it's basically this like a warehouse scale computer, right? And then data centers, the problem that they have is they are too big, right? So you need to partition the data center in smaller failure domains, right? Like we see in this slide, you have a couple of data centers that they are in a campus, right? So they're just sitting one to each other, and they are going to have like different machines organized in different clusters. So for example, when there is a fiber cut, you might have different fibers per building. So you lose only one fiber, or one fiber that like feeds one data center, and therefore that data center is disconnected, but the other one in the same campus is still operational. Within the clusters, you might have different logical groupings of your machines. So when you, for example, deploy updates of the software of these machines, you do it in groups. And if the update then turns out to be bad, that is triggering an outage, right? Then what happens is that these machines, they are out of service, but the rest of the fleet that you have there is still functioning, and you can still run services in there, right? The data centers, for example, in a company as large as Google, we are going to have tens of data centers across the globe, right? We're going to have like a bunch of them in the US. We have like many in Europe. There is one that is super large in Belgium, another one in Finland, for example, that you're going to see. And then software engineers will distribute their software within the data centers. As you can think, we just don't offer data centers raw access for software engineers to deploy. Like we have platforms for deploying and develop software, right? Because otherwise it was going to be unmanageable for the number of machines we have. So there is another trend and another discipline that is called platform engineering, that is building these platforms for developers to build on top, right? And make a very efficient use of all these resources that we have. So all these data centers, they are managed by Borg. If you know Kubernetes, basically Kubernetes is at the standard of Borg. So Borg is just a cluster management service, right, that we use to manage machines. One cluster of Borg can have tens of thousands of machines. And then what we have is a Borg master. Then we have like scheduler. So if you are familiar with Kubernetes, you would see that the concepts are exactly the same. But basically what happens is like each of the machines, we call it the Borglets, right? And they're going to be managed by an scheduler. So whenever you request a Borg cluster to run a job, you're gonna be like contacted to the scheduler. They know exactly where the resources are, how much they are utilized, and so on, and they're gonna find an optimal solution for like where your job needs to be scheduled. So it's gonna like give you a machine, and then you can just run your stuff in your machine, right? This makes like a very optimal use of the resources that we have, right? And then the nice thing is like the scheduler, when a machine breaks, is going to move your things around, so virtually is always running for you, right? The scheduling and the design of this service, the Borg, is a big data problem by itself, because you're going to have, tens of thousands of machines. You're going to have like millions of jobs that they're going to have to run in here. So just the scheduling, for example, is hard and is dynamic, right? Because the machines, they are going to be changing all the time, right? And then you are going to need to design it for high availability, right? So your Borg master needs to be always accessible for like mutating your jobs, adding new stuff, and so on. So it's like a fractal of complexity in a sense. So that's for the reader for later. Like basically like a Borg job, a Borg cluster is a collection of machines, and then there is a scheduler that will just place jobs here and there for them to run and for you to do stuff. Things that they are very complicated is storage. If you have worked with large amounts of storage, you are going to see that the storage has two problems. Is accessing storage is not as easy as it looks like, because you're going to need like large amount of bandwidth to read large files, for example, for you to do like analysis or for like a training models and so on, and then write them back and do inference and all that stuff, right? And second, storage is non-fungible in the sense of like if you have a file that gets corrupted, you better have a backup or another copy, because that's usually like unrecoverable, right? So you're going to need to think that when you lose machines that contain data, you're going to have replicas all over the place. This is why we have cluster file systems. So what we have is a thing that is called Colossus, and what it does is transparently will just put copies all over the place, and it's going to do like recovery and so on. It's basically like a RAID, like redundant array of independent disks, right? But at larger scale. And then we have networking. How you connect 100,000 machines, right? So for the networking, we have different types of networking. This Jupyter thing is one fabric that we have in the clusters. It will have 1.3 petabits per second of aggregate bandwidth for the cluster. So machines can communicate with each other, and they do not have a bottleneck in the network. They will have a bottleneck in other places, right? And then B4 is the backbone. So you are going to have to connect all the tens of data centers that we have between them to exchange information, like for the different jobs that they are going to be running across data center, right? But as well, we are going to need to connect to the customers. So we are going to need to connect to you, to your phones, to your devices, and so on. And what we have for there is like our backbone is connecting different peering points with ISPs. Like Deutsche Telekom, Telefonica, all that people, they are connected to us in different exchanges points, like POPs, right? And then we reach you, or you reach us with that connection. Like you just go through your ISP to our backbone, and then you just are routed around to where your YouTube video is lying, right? And that needs a whole lot of software on top, like for example, load balancing. So the question of load balancing is very easy. It's like, okay, given a user, what is that wants to do like some request, or wants to like operate into some of the services, where do we have to take them, right? And that's an easy question, but it's a very hard answer, because like, you are going to want to take them to the closest place where the data or the service resides, right? So the experience is really great. You are going to want to as well move the users around, so the infrastructure is protected, in a sense of like, you don't want to overload places and have underload in others, right? And you are going to want to have flexibility for developers to put services in the platform, and then being discovered by the users like easily and safely. So you don't want to expose all the service that we have internally. You just want to expose like different things to the users and make sure that there is some, like order access to them, like there is authentication and all that stuff. And then we have how we just go deeper, right? So what is the next thing? How do we communicate to services? So once you have all the data centers, you have all the networking, you have all the storage, and you have load balancing in a sense that you can have me loading a YouTube video and being connected to one of the services that we have. Is like how you communicate that two elements, like my app with my server, right? So we have one thing that's called Stabby. If you know gRPC is like the new thing. Like it's the succession of Stabby, but basically it's an RPC framework. An RPC is a remote procedure call. There were like older versions, how it's called the XRP, like the one from Sun, all these things over time. Corva has been another version and so on. So over the ages, we have different versions of them. Stabby is basically one that is super simple in the sense of like it's just moving protocol buffers. Protocol buffers is just a binary serialization of data, structured data, right? So it goes one way, comes back the other, uses HTTP, very easy, very lightweight, very fast. And then, well, you're going to need to develop your software on that, right? So you are going to have, for example, a code repository. So we have one repo. We use a mono repo, so everything goes into the same repo. No like Git repos like lying around. We have a couple billion lines of code, and then we have things like, for example, continuous testing, things to continuously build our binaries, things that do compliance, like for example, for the making sure that there is no vulnerability. So there are scanners for code safety. There are scanners for code quality, large scale changes. All of the thing goes in there, right? And this is just to develop the software. So whenever you go into doing something at production scale, you're going to need to figure all things out. Like every company, they will have answers to all these questions as well. Google will do it like that, but if you go to Meta or if you go to a bank, they will have different approaches for solving all of this. But this needs to be resolved. So this is how a service at Google internally looks like. So you are going to have your users, right? Then they are going to go to the Google DNS server. So that's the first layer of load balancing. So we're going to know that you are connecting from Germany, for example, and we are going to route you to, let's say, Belgium, for example, because that's the biggest data center that is close enough for you to have a latency that is decent. So you are not going to Japan in that sense. Then you connect to that GFE, there's the Google front end within that data center, right? And then the GFE will be informed by the load balancer saying like, okay, this user wants to load like Gmail, right? Where it is, right? So the GFE will just go to the application front end, and then the application is going to be like, depending on the application, they will have different shapes, right? So if you know things like HA proxy, that's very similar to the GFE, right? It's a reverse proxy. Nginx, all these things, they are similar to that, right? So you can deploy something that's very similar with open source, for example, if you wanted to, right? And then the application front end, and then the databases, that depends on what it's doing and what is the shape. It will have different structure, but mostly is the same, right? So now we go to risk, right? So that's the basis where we operate, right? If you operate in a cloud like AWS or GCP or Azure, it's going to be the same. It's going to have just different names, but you are going to have the same building blocks to build your application, right? So how do you measure reliability, right? So how you know how much are you reliable, or how much are you, fulfilling the goals that you have? You need to measure that, and you're going to need to instrument your services. There is a whole discipline that is called observability that you are going to have to learn about, right? We're going to go through it as well. But basically, measuring reliability is something that is not hard at the beginning. So it's like availability is how much time you are available out of the whole time, right? So if you divide the proportion of time that you are available divided by the whole time, meaning that uptime and downtime, that tells you like a ratio, right? So that's how much availability you have had in your whatever time window you are using to measure it, right? This is very intuitive for humans, but this is very hard to measure for machines, because how much uptime does a service that is running 10,000 machines has, right? You really can estimate that directly. So what we do is an approximation, right? Before we go into that, I want you to read this slide, right? This is something that will allow you to grasp why it's hard, right? So, for example, let's say that you have a service that is aiming for 90% availability, meaning that it can be in downtime for 10% of the time and just be fine because your target, your goal is to be 90% or more, right? So every month you might take the service down for 3 days and be okay, right? So there are many services, for example, in banks that they have these properties. So there is no banking operations, for example, on the weekends, right? That doesn't mean it's not important. Banking is really important for society, right? So there's no doubt that you cannot have a functioning society without banks. But it's true that you are not going to be executing transfers on the weekends, right? So you might have banks as important as they are with a 90% availability, right? And say like, look, during the weekends, we are going to take these services out for maintenance, right? So you just turn them down, do what you have to, and then turn them back, right? And then as long as you are only using 3 days a month, you're going to be fine. You're going to be meeting your targets, right? Then there are going to be other services that they have to be available all the damn time, right? For example, this is a service that has 5 nines. 99.999% is 359, right? So this would be 90% is 19, and this one is 5 nines, right? Every day, if you want to have every month, if you want to have an availability of 5 nines, you can only take the service down for 25 seconds, right? So a couple of examples: services that they are in GCP, typically they are aiming for 5 nines for you to build on, right? So you are going to need to design on top of GCP, right, to be budgeting for like the possibility of a service being out for like 30 seconds, right? Services that they are more under the stack, right? For example, the authentication services that we have, some of them, they would have more than 5. They would have like 6, 9s or more, right? Because many things depend on that. So you cannot aim for them to be down, right? If you look at the progression here, every time you add a 9, for example, you go from 90 to 99, right? You are dividing by about 10 the risk or the budget or the amount of time that you can be down while meeting your objectives, right? So you go to 99, then you add a new 9, you divide by 10, then you add more 9, you divide by 10, and then you divide by 10 again. Divided by 10, your unavailability budget, which is this window, right, means that the service is probably be 10 times more expensive, right? It's going to be much more complex. It's going to have much more replicas. It's going to have much less tolerance for risk, right? So choosing here the availability level, you should always choose the lowest availability level that you can afford. So then how you translate that into machines? So what you do in systems that they are transactional, like the majority of the systems that we have in the internet, is using an approximation based on the request count, not by time, but request count. This assumes that you're going to have like a constant amount of requests, which is not really true because the load will just vary over time, right? A service will have a load profile that in the night typically will have less demand, right? But anyway, you can do that as a very nice approximation. And then what you're going to have is like the total requests that you have processed, right? How many of them they are successful, right? And that's your availability approximation. It's really, really great approximation, right? You can apply it to distributed systems. You can apply it to batch processings. It's true that not all the requests, they are the same, right? So in the world of banking, for example, maybe it's not the same or it's not as important for the bank to be able to do transactions for existing clients, right, than to open new accounts, right? A transaction for an existing client might not be something that you can wait on, but opening an account, you can tell like, well, just wait an hour and you will have it done, right? Because it's an operation that you do once during the lifetime of the client, right? And then there is the trade-off of reliability versus result velocity that was mentioned before, right? Generally, the more reliability you aim for means that your budget, right, your allowed unavailability is going to be low to the point that is nothing, right, or almost nothing. It's never going to be zero, but it's going to be like asymptotically going to zero, right? Means that you are going to be able to tolerate less and less and less risk the more availability you target. Meaning that you are going to have way less velocity for developing. And that means because you are gonna have to do, for example, your rollouts of new versions of your software, you are gonna need to qualify them more. You're gonna have to have more test coverage. You're gonna have to have integration tests. You are gonna have to have rollouts that they are super slow to validate with different, like a small amount of users and so on, right? basically to reduce the main risk, which is the system changes. Like the more reliability you are going to want to have, probably the less changes in the system you are going to be able to tolerate in your function, in your product, in your service, right? And then there is the cost, right? As I was saying, like, 1.9 is slashing by 10 the number of errors that you can tolerate, right? And every time you do that, there is going to be like more complexity going on, right? So how you choose? Like there is like some guidelines here for you, but basically choose the smallest that you can afford for your business, right? For your product, for what you're doing, right? If you're doing a prototype for, like some research thing that you are going to launch in the community, probably you can afford having less reliability, right? And you are going to have a system that is much more simpler and maintainable, right? If you're doing something else, you're going to need to go up, right? So now we're going to failures of distributed systems. So when you have distributed system, you are going to have an important amount of components. It's not going to be only what you write, but it's going to be as well where you put it, the platform what you are building it, right? So that is something that you're going to need to choose carefully, right? It's not the same building in bare metal than building in a cloud. It's not that bare metal doesn't have failures or the cloud does or vice versa. Is that they have different types of failures, right? There are going to be failures that they are global, meaning that your whole thing is out, right? There are going to be failures that they are going to be affecting only a region because that part of your infrastructure is affected, or only a set of users, right? Because they have a different configuration parameter, or they are placed in the different database, or whatever it is, right? You are going to have outages that they are like boom, like service out, you fix it and you're okay. And then you're going to have errors that they are like what we call in general the slow burn. So like a small amount of background requests that they are just failing all the time, right? That costs you availability, and it will cost like some services that they are offering a not great experience for your users, and you probably want to look into them as well, right? And then you're going to have the ability to do graceful degradation if you design the system with that. Like for example, if you look at Google search, there are many things going on when you do a search. You get the results, but you are going to get like knowledge graphs, you're going to get like an AI summary now, you're going to get like images, you're going to get a map, depending what you're looking, right? There are two ways to approach that. If something fails while you are processing all that, one approach is to say like 500, I'll just yield an error to the user, I'm good, have a good day, right? Or if you want to, protect the experience a bit, what you can do is like, okay, I couldn't get a map because the maps services is broken, right? So I'm going to present just a page that has all the components, but not the map to the user. So at least, it's not the full experience, but is a response to the request, right? There are things like Bing, I don't know if it's a hand or something, or is in another place. It's in another place. Good. So sorry for the interrupt. And then there are things like planned maintenance, like things that, for example, banks or other institution they can afford to do, because there is some places where sometimes in the week where they don't have business, right? So profit from those. If you can do things in the weekend, oh boy, like that's fantastic, because then you can take all the risk you want over the weekend and then just leave the system static over the weekdays, right? And then there is the cost of failure as well. So you can there is one thing that we do whenever we have an outage is calculate the financial impact of that incident to our business, right? And then you can calculate how much is the cost of things, right? So if you want to say like, hey, we need to go from 3 to 5 to 3 from 3 to 4 nines, right? We're gonna slash by 10 our error budget, right? How much money are we making with that service? 1 million. Okay, fantastic. If we improve our availability by 0.09 percentual points, right, means that we are going to get probably an estimate maximum of $900 in revenue for a service that is doing $1 million a year, right? So if you can implement that increase in reliability in less than $900, right, go for it. If it's going to be more than that, it's not economically sensible to do it, because you're going to spend more money into what you're doing than what you're going to get back from the service revenue. Well, this is for you. There are many other service metrics that you can look: availability, latency, blah blah blah. There is the golden four, that is the resource usage, the availability, and the saturation kind of thing. We'll see it in a minute, right? But that gives you a sense of like starting point. Then, depending on what you are doing, the metrics that you are going to have to take, they are completely different. And that leads me to AI. So now there is a way that, or a thing that we have not done as an industry very much, that is measuring quality, right? So we have all the time had systems that they are binary, either the response is correct or not, like you are authenticated or not, right? So if you request an authentication and you want to get a credential, or you want to send an email or whatever it is, right? There are three states. The thing was successfully done, you are not authorized to do it, or it was rejected for reasons, right? It's like you cannot do that, right? Or the request legitimately just failed, right? When you have systems that they have AI models in the middle, right? The answer might not be binary anymore, right? You are going to have like a scale of grace all the way from like the answer was canonical, it was correct, it was perfect, right? To the answer was existing, but the user didn't like it. It was not sufficiently verbose. If you are like, for example, thinking about like a chatbot and these kind of things that they're very popular, right? It didn't produce the image that I wanted or that I was looking for, right? And it's not that the system is not working; it's working, but probably it's not working as expected. So all these measures of quality, right? We are going to need to incorporate them in our toolbox for production management, precisely for understanding how the system degrades, for example, right? How we can, measure the impact on quality of a new deployment of a new model that we're doing, and so on and so forth, right? And that's where we go for the objectives for the service level, right? I think you might all be familiar with this. Service level indicate, well, SLAs maybe not, but I think SLAs, you have surely read about them. It's the service level agreements, right? Like whenever you contract with some service provider or whatever, there's going to be, this is the SLA kind of thing, right? But then there are more. There is the service level objective and the service level indicator, right? We're going to look into this because this is how we summarize the quality of service and how we can just generalize like the service quality and the service properties, right? So what is an indicator? What we were discussing before, basically the proportion of requests that they are successful. But you need to define what is successful, right? And successful might not be just we responded to the user with what they wanted, but as well we did it in less than 500 milliseconds. We did it with, like, if it's going to be a storage system, we are storing the code or the data that we need to store with so much durability, in the sense that it's never going to be like deleted or whatever it is, right? And so on and so forth. Or there is going to be the quality of the responses that we have. We are going to have a measure of the user feedback, or we are going to have like an automatic measure of like, verboseness, or like a similarity of different responses between the different users, and so on, right? So all that stuff is something to consider for your indicator. Once you have all these properties, right, the indicator is going to be like a time series that you can just watch over time, right? It's going to be like a number that evolves over time, over the usage and the evolution of your service, right? And then you're going to have to see like where you want to take that, right? So how high you want, or how low you want to take your service level indicator, right? So once you have the aggregate indicator, it's like, okay, typically they go in like rates, so like ratio, sorry, it can be from 0 to 1 or a percentage, right? For being like, they are easier to reason, but it could be any number, right? But then you have to say like, what is my objective? Like when I am done in terms of quality, right? So you're going to need to find a target with the hints that we were discussing before, like how this is important for your service, for your business, how this is costly, like, many different places. And then you say align and say like, my objective is whatever, right? So if I specify my SLI in terms of like a rate, a ratio, sorry. Then I say like my objective is 3 nines, 99.9%, right? Then it's easy to know if you are done or not. If your indicator is over the objective, you're good. If it's under, you have work to do. It's as easy as it is, right? Depending how high and how low you are, there are things that you need to think about, right? Because surpassing the SLO by too much has problems, as you will see in a minute. right? And then the problems is like when you're under, is evident that you are not meeting your objectives. But when you're too high, right, it has a problem as well, in the sense of like you might be overperforming. I know this is paradoxically, but when you overperform, you create expectations in your customers, right? In your clients, in your users, right? And then you might have a failure, an outage, and it's like, well, that was planned. I'm targeting 90%. I have like 3 days per month. I had a 24 hours outage, right? That never happened before, and your customers are complaining because like, hey, I built my stuff around you being available all the time. This is what happened with Chavi. Chavi is a distributed log system, so it's like a Zookeeper if you have figured or like use it in the past. Is like Raft. Is like it's built with Paxos, as a matter of fact. But basically, it's like what allows is the following: when you have different replicas of a service, right? You want to elect a leader of those, right? Chavi helps you with that, right? So you might have hundreds of replicas of it, and Chavi will say like, well, this is the leader now. So if you want to contact it or do mutations or whatever it's what you want to do in your design, you just go contact that one, right? And when that task or that replica dies, then Chavi will help you elect another one. So there is always like a leader for your replicated service, right? Chavi is a very simple service and it's available all the time, but it doesn't have an SLO that is too high, right? I don't know how much it is, but it's not like many nines, right? And then many services start to build on that and assuming that Chavi was going to be available forever and ever. They had an outage and there was a problem, and then you have two options. That is, A, well, let's commit to the SLO that customers were expecting, right? That was so high that it was so expensive that it was nonsensical, right? Or let's do the following: is like, fine, let's take the service down on purpose so people understand that it's going to be down so much time, right? So this is what we do. Chavi, we take it down from on purpose to just have the SLI close to the SLO, so the services that they're building on top of that, they understand that this level of availability can happen, right? So we just like take it down for a few minutes, like every other week or every other month, and then like everyone knows where we are, right? This is done in order for the service not to get too complex or too expensive, right? And the customers building the reliability in the application, which is where it belongs. And then you have SLAs. SLAs basically is a contract, right? So once you break your SLO, right? So you say like my SLI goes down, what happens, right? It can be nothing because it's an internal service or whatever, or if you have something that you are offering to customers that they're paying for your services or whatever, you might have to give them a compensation, for example, in terms of like budget or whatever you agree in this contract. Typical indicators for you to know. The classic is the availability, latency, and throughput. That's a classic. Databases, like transactional services, banking stuff, that's a classic. But if you go to things like storage, then you're going to have durability. If you have big data systems, like for example, my favorite is BigQuery. I use it all the time, right? So you have tables, you have a data lake, you start doing queries, all the crap, right? You can do a lot of insights. That's fantastic. But I really don't care much about availability, right? I could have a BigQuery that is available 80% of the time and be fine with me because I use it when I'm at work or whatever. So it's not something that is being used, at least from my perspective, from all the time, right? Other customers, they will have their own view, right? But I do care about the throughput. For example, when I type a query and the thing needs to analyze like a couple billion rows, right? I want that to be as fast as possible. Right, so it's going to take a few seconds. Fine, that's okay, right? But I want the system to be like using the resources efficiency for me to see the results like really near real time, right? And the latency. So if I type a query and the system is congested and I have to wait in a queue, that degrades my experience. I don't like that, right? So we're going to have indicators about that fact. There is correctness and so on, and then just keep it simple. Okay, then we go into like more detailed kind of stuff. I think I'm going to skip this because we have like 40 minutes to go. And I want to cover something at the end. One thing that I want to tell you that you need to know is that things are not singular numbers, mostly never. They are all distributions of things. So you are going to need to understand well distributions that they have a long tail, like exponential distributions, Poissons, all that stuff, because that's how processes in production really look like. right? So when you have an analysis of like what is my request per second, there is a temptation of doing averages, like using like means or even medians, right? It's not great because it hides too much the behavior of what is really happening behind the scenes, right? So I'd recommend you to understand statistics really well because it's nice and it's super useful for everything, right? But the modeling everything as a potential distribution, right? Because then when you have a distribution like the example that I have in there, which is the crappiest distribution drawing that you might have seen in the history of drawings, right? You would see that there is like a tail, right? And the tail is super important, right? It's not the same saying like I want 99.9% availability in less than 5 milliseconds than in less than 5 seconds, right? That's completely different, right? And that encodes all the tail that you are going to have in your service, right? So think about the processes as slightly more complex than what average are gonna tell you about your service and your product, right? So that leads me to monitoring. Any questions so far? I have covered quite a lot of things. So no questions? Good. There is one chat. Wait a minute. Let's see. So Omar asks, regarding system incidents, what are some recent key lessons from your postmortems that have led to significant improvements? Oh, that's nice. I can spend an hour now on that. Like a great question. So when we have an incident, we do a postmortem and we analyze what happened, right? The postmortems, this is something that's going to be covered in the later stage of the talk. I think we are not probably have the time, but I'll give it to you and then you read it. But it's like the following. We go and do an analysis that is structured and we say like, okay, this is the root cause, this is the trigger event, this is the timeline of events that happen, and so on. So for example, in the outage that I was explaining before, let's use that one as an example. You're going to have a start of the outage that was not when the trigger, when it was visible. It was much earlier, right? It was when the database schema changed, right? So you just submit the change, it executes, and that's fine. It's just latent, right? It was not triggered just yet. I don't know how many times happened, but it was, let's say it was a few weeks. Then someone runs the batch job that was expecting the other schema. That's a triggering event, right? And that's when the outage is visible because it's now affecting your service and your user, right? And then there is a whole lot of mitigation steps and so on. So that's what is a postmortem. So the postmortem is not about who did what, but how to improve the system so this failure or this class of failures never happens again, right? It's never a people problem. It's always a system problem, right? Things that we have learned, for example, plenty of things. First, one lesson that we had is like testing databases, particularly schemas, is very hard, right? It's very hard because databases are not, you deploy a database, for the first time you have a schema, it's just there. Schemas keep evolving over time very often, right? And those, they keep giving like some sort of baggage in the database of like meaning, assumptions, different like defaults that the fields used to have and so on. So testing that is hard. It's something you have to do, right? And as well, you're going to need to have things like data integrity and so on. Other things that we learn is that we don't live in 2005 anymore. And I explain what that means. For the evidence. So in 2005, 2006, up to the 2010s, 12, like when the cloud started to ramp up, right? We lived in a place where designing global services was what we needed, right? So Google search is just one, Gmail was just one, right? So the implications is like, customers are expecting just one service. So it's going to be global in a sense. So it had many components that they were quite replicated, but they were logically like one functionality, right? When we started moving computing or customers were moving computing to the clouds and so on, we started discovering that this was not cutting it anymore, because now you need to have different regional instances of your services. You're going to need to have partitioning. You're going to need to have availability zones. You're going to need to expose this to the user as well, to the cloud client in this case, right? For them to build services that they have failover on their part and so on, right? So that's something that we learned that is now the norm. So that's all the services, mostly all of them, they are now partitioned like that, right? Other thing that we study as well in this is something that's ongoing. So there are many of them. But other example of things that we learn in postmortems that they are very very interesting is the cascade failure. So a cascade failure is when a small thing makes other system or other component fail, that makes other component fail, that makes other two component fails, and so on. Example. So data center in the United States, there is a fiber going into the data center, right? There is a construction work. There is an excavator, breaks the fiber, right? Well, it's a fiber, right? What happened? So there is some, replicated database and so on in the cluster that is affected by fiber cut. This cluster is completely cut out. So it's out of service, right? It's completely disconnected, right? Some system cannot access the data that was replicated in that cluster, right? Start service 500, right, to the users. So errors, like users, like it was, I don't know if it was, I don't remember, it was an app or it was like some website or whatever, right? They were just retrying in other locations. These locations don't have access to the data, therefore start failing. These customers go to another location, start failing as well, right? So just one fiber cut, due to the design of the system and the application on the customer side, right? It was just slowly killing all the different deployments that they were touching, right? That's what is called a cascading failure, right? So now, for example, over the years we have learned how to design systems to prevent these cascading failures. So if something has to fail, fantastic. Well, no, it's fantastic, but like it failed. That's okay. But at least it needs to be contained in a blast radius that is not going to go outside of that, right? So this is a skill that SRE has built, and that mostly like all developers need to build as well when they are designing applications. I hope this answers your question. If not, just go for it. Yep, blameless culture, effectively, yes, 100%. I lost my slides. Well, they are here. So how you monitor all these distributed systems? This is not just looking at them. You are going to need to look at many things, right? So what is monitoring? First of all, disclaimer, when I say monitoring and observability, I'm going to use them as the same term. Is by no way the same thing. Like monitoring is just looking at time series and all that stuff. Observability is something that's much more complex, and it's something much more interesting because you're going to look at different things like traces. You're going to look at FAT events. You're going to do many things post facto. So you're going to be, if you look at observability in general terms, you're going to collect a lot of data about how the system behaves to study it after the fact, right? To see like how it works, like to discover new insights and so on. Monitoring is mostly a priori, in the sense like I want to monitor these time series, like these are the properties that I want to look at, right? And then you define them, expose them, collect them, and that's all you can do. So take it with a grain of salt. So, like, I'm only going to cover monitoring for the time we have, but don't go there until like monitoring observability, because it's not. So basically, what you want to know is how the system is performing in real time, right? Your SLI, but as well many other things like usability of CPU, resources, like latency for the users, where the traffic is going, like all that stuff, right? So why monitoring? Well, you need to know what you are doing basically in your system, basically, but there is all these use cases. You want to monitor things in a nice way, so build dashboards and alerts. Alerts they are like so you don't have to look at dashboards all the time, right? So you get an alert and it notifies you like when things are broken, right? And this is where I wanted to go. And this is something we learned, by the way, with the postmortems and so on. That is the following: symptoms and causes. I think that's a very important part, like doing causal analysis or doing just a symptomatic analysis. So what is a symptom? We are serving errors. That's a symptom, right? It's not the root cause. Serving errors is the product of a problem. You want to understand what is the problem, not the product of it, right? Slowness is another symptom. Users in Antarctica aren't receiving what they have to, and so on, right? Those are symptoms. Symptoms, to be fair, is the only thing that you're going to be able to observe in the system, right? So the symptoms is like the diagnosing a patient. This is what you see, but you don't know what is the virus that the person has, right? So what you need to go is from symptoms to causes. So there is a lot of causal analysis, and there is a lot of theory, and there is a lot of practice, right? To go from, like, for example, I'm serving errors to the database is refusing connections, right? That could perfectly be the case, right? Or if your responses are slow, maybe there is some bottleneck in your system, CPU network that is congested, whatever it's going to be. Or people in certain places are not receiving your stuff. Maybe your CDN is disconnected, right? Because there is a fiber cut with Cloudflare in some place, right? And so on and so forth, right? Think that as well, security and availability is very much the same problem in a sense, right? So you might have things like private content is readable, like that's a vulnerability issue. So it's not an availability in that sense, but the cause is that some ACLs, that is access control lists, they are misconfigured, right? That's a problem for the system as well, because if it's exposing private information, probably is not working really well. And then you're going to want to do things like a white box, meaning that you're going to be looking into the internals, or black box, which is you're not going to know exactly what you are looking for, but it's the most similar to what the users are going to be seeing from your service. So it's very useful as well, because you're going to be able to look at the product that you have the same way as your customers are doing, because your customers, they are not going to know what your database is going to be. And then you are going to have to do root cause analysis. Root cause analysis, what I was mentioned before, is a whole technique and a lot of theory that goes into going from symptoms to the root cause. So this is not done randomly. Whenever we get an alert of things are broken or an SLO is not being met or whatever, there is a whole structured process to go from the symptoms to root cause, and then to do the analysis of like how we can solve it and how we can improve the system. Skipping that, skipping the tail, we go to automation, right? So, automation. What is automation? Why you want to do automation? Automation is the only way, right, that you are going to be able to go from pets to cattle, right? It's the only manner to do it. And automation is not, many people think of automation about writing scripts that they encode a process that you had. So for example, you have a process for doing releases, right? You just encode it into a script, right? The best automation is the elimination of that process. So you don't have to do it anymore. Neither you or neither a script that you're going to be running in some way, in somewhere, right? So, or changing how the system behaves, right? Instead of having to do like, fail over with the script automatically from each other, you might redesign your service so you don't need that, right? The thing is like designed so it finds your data automatically, or it's just replicated or whatever, right? So think about automation from the point of elimination more than the point of like automatically running what you have. So value of automation, I think, is just clear. Like, one is consistency. So I think consistency is something that is very important when you run at scale, because you are going to think that you are going to have a whole lot of things moving in your system: components, binaries, many things like databases, schemas, batch jobs, like training models, and so on, right? So consistency is important because then you are going to be able to manage all your components in the same way. Like, for example, if all your services, they are written with the same framework, all your databases, they are using the same technology, all your stuff is written with the same compiler, whatever it is what you do, right? That gives you a consistent view of things, and it's just easier to understand, right? You don't always can do that, because at some point you're going to need different types of database for different types of data. That's okay, right? But try to minimize. Then you build a platform. We were speaking about platform engineering, right? That's a nice automation, because it's meaning like you just offer your developers like the same thing, and everyone uses the same platform. So when you get there, it's like a way to globally move things around, right? So if everyone develops in Borg, for example, when we need a new feature for security purpose, we just code it in Borg, and then everyone automatically just benefits from out of it. That's automation as well. Well, faster repairs, okay, of course, because you when you think about a problem, it's always the same kind of thing. So you don't need to reason about what it is. You only need to go directly to the problem that you have at hand, right? And then, well, faster action, same thing, time saving, blah blah blah. So I want you to give you an example of automation that is not writing scripts, right? And it's the original Google infrastructure and Borg. We saw Borg before. That is, la general cluster management and so on. The original infrastructure was machines, and every team had their own, like, I don't remember what it's called. It was called nanny, I think, or something like that. But basically it was like machines, and then people deploying the machines, and you SSH to the machine, and you need to remember where your thing were, and then to move it and so on, right? So it was super time consuming, right? So the thing is like the bringing Borg, right? This was not writing scripts. It was moving people to a common platform, right? Which is automation as well. So when a company is running their own servers and so on, and they move to the cloud, basically it's the same thing. They are moving to a common kind of substrate. So the assumptions, the features, the knobs to configure it and so on, just becomes the same for everything that you run on top. Good so far? Maybe we are going to make it after all. Anyway, so let's continue. Then release engineering. Why I'm covering this? I'm covering this because like the large majority of outages and incidents that we have are because of changes. And I'm covering this because with the AI-based systems, releases are going to change substantially. So what is releasing something, right? So releasing is you have source code, you want to have binaries in production serving to the users, right? There is a whole journey for that, right? So you are going to need to build it, right? You are going to need to integrate it. You are going to need to qualify it. You are going to need to get a built asset and now figure like how do I take it to the multiple data centers or whatever it is, right? Safely, right? And you are going to need to restart things and you're going to need to move things around all the way, right? So it's important that this whole process is repeatable, right? Because if you make it repeatable, you are going to have two properties. First, you can repeat it, meaning you can run releases as often as you would want it, right? And second, if it fails, a repeatable process is something that you can audit and you can edit and you can see where it fails, right? So you don't need to like do a slow thing of like oh, where this can fail, right? You can go step by step, seeing like what was different and what failed, right? And then you can have the repetition of it, meaning that you can achieve high velocity. You can have multiple releases going a day, for example, right? If you wanted to. There's more releases you have, the difference, I think this is well known, but the difference that you are introducing in each release is smaller. Therefore, the risk of each of the release is smaller too, right? And then when you need to roll back one because that's broken, you don't move back like weeks of work. You just go back like a few hours. So this way, having repeatable process is very important, right? Policies and so on, right? And this is where the interesting part comes in. So building, you need a build tool to convert source code to binary. Understood. Branching. Now, this is a policy question. It's like, so whenever you are going to do a release in your repository, what do? You create a new branch, and then you can just keep piling like patches in there, and there's another branch for the trunk, and then you merge. You are going to release from the trunk, right? Neither is better than the other, right? You can do both. Depends on the environment that you have and how you want it, right? There are pros and cons, right? And then I'm going to touch a bit about AI in here. So when you release things to production, you can release many things. You can release a binary, we all know, you compile it, or it is a jar file or a C++ compiled to a binary, whatever it is, right? And that's, you just execute it, and it's a process that is running, doing things, right? But there are many other components that your service will have. They don't have configurations, for example. Configurations, you don't compile them. It's just a file that you push to places that has, parameters for the service. That can be wrong as well. So you don't need to have a process for validating these configurations. There is as well things like assets. If you have a front end, you're going to have like fonts, you're going to have images, you're going to have JavaScripts, all that crap, right? So all that needs to be as well qualified. If you have you're training an AI model, right? You are going to have another properties. It's like imagine that you are doing a service that will just serve a model that is a fine tune of your favorite thing, Mistral, Gemini, whatever is what you use. You want to do a fine tune for achieving a specific task, right? And every now and then you want to update your fine tune because to have more features or whatever it is, right? You're going to have to deliver to production an asset that is a binary file with the weights of the model. You have to put it in production and then you inference out of it, right? What happens with the model? You're going to have like a base pre-trained, then you're going to have like a bunch of fine-tunes that you're going to be doing, right? You're going to need to have traceability of that, right? Because you're going to say like, hey, the model I have in production, right, was a fine-tune with this data set that was done in this GPUs or these TPUs or whatever over this base pre-trained model, right? And then you discover that there is a problem, then you want to trace it back. So you're going to have like some certain like traceability of all these things. What is the data that you're fine-tuned with? What is the pre-trains that you have? Are you going to have to pre-train the whole thing? Are you going to have to like do a new fine-tune? Are you going to have to change your data sets, right? So the production of ML models into production, right? So the creation of these models back to production, it will have all sorts of processes and data governance and data lineage and all that stuff. And with regulations that they are coming up, even more, because you're going to need to even, like, for example, at some point, even certify data that is in the model and is not in the model. This is something that's very, very, very similar with what we do with repeatable release engineering, right? It's something that is a process that is mostly the same. So, simplicity. This is, I think, the last part of what we want to, or I wanted to cover today. There is more things, as I say, you can read it by yourself, and you feel free to send me questions if you have to, right? But the most complex systems are the ones that they are more unreliable, right? And you see it in every system, like things that they get bloated and things that they get like tons of stuff, things that they get an architecture that gets out of control, right? They start having problems. And these problems, they start to become harder to solve because reasoning about the whole system is harder, and therefore you need more time to solve it and patch it. So we are going to need to see, and you're going to realize that I'm always doing this, like, dichotomy, V for stability, reliability, and agility and velocity, because it's the whole thing, like, and it has always been since the 70s. And I think it's going to be forever, right? The more reliability you want and the more stability that you want to have for your system, the less agility, the less change, the less hysteresis, the less entropy, you can call it whatever you want to introduce to the system, right? So one way to achieve more stability while keeping some agility is minimizing the services, right? So have less dependencies, have less components, run on less platforms, use less software, right? So don't depend on these many things. Like there is a joke that and this is true, the npm, the Node.js, like this npm package that is called isOdd. So it turns out that there is a package that is called isOdd that you will give it a number and it's going to tell you that is odd or not odd, like the number. There is a package for that, right? It's downloaded like 100,000 times a month or something, right? So that's a dependency that you can cut in your system, right? Because if that package gets, for example, compromised, right, you are going to be just having to like fix that compromise, like in your pipeline or software delivery, right? So the less generally is the better, right? So lean system, like think twice before adding new dependencies, new components, like splitting things, like that's something to consider, right? And then there is the something some people call it boring. I call it stable because it's just more, less harsh to people. But if you work in infrastructure, right, if you do well your job, no one knows that you are there, right? If you have an infrastructure that is stable and so on, there's going to be a lot and a ton of work going into it to be stable and to build, like, workable, and to have like indicators and to have like, the features that you want and so on. But it always works. So no one remembers like the SREs or the developers that they are behind that, right? That's your success. It's a bit of a paradox because no one is going to celebrate that, but people is going to come to you when you have the outage, right? But that's a goal for running large scale systems. Like no one remembers how large or how complex it is. Like whenever you have a large scale system and you have something that is as complex as BigQuery is, right? The user interface is basically a prompt you have in your console, and you can type queries, and the thing is going to give you data. It's a very simple and very neat kind of interaction that you have, right? It has tons of components, right? So when you run your thing, you see like it's going to process like a couple billion rows in 3.5 seconds. Here is your data. Have a good day, right? That's what you want to be with systems. Yes, don't count code, but count the code that is deleted. That I love that. Minimal APIs, that's all for you. Modularity, there is a whole lot of a discipline of like software architecture, like, like quality. There is like many books. Clean Code is a great book that you could read. There is one that is the Systems Bible from John Gall. That's another one that is very nice for understanding these whole things. I recommend you those. And then simplicity. So I could cover, let me see, because this is troubleshooting and probably you don't want to do the troubleshooting. This is just the method of the how to go from a symptom to a root cause, right? I think I'm going to leave it to you for reading, but basically, remember that correlation is not causation, but please do use correlations as a hint to go to where you want to go. Example this. So correlation is not causation, but if you have this correlation, maybe you need to look into that, right? So here is one thing that I wanted to cover, that is the post-mortem thing. Good, because there were questions, so I think this is going to be interesting. But basically, this is where you want to go. Fix root cause once and for all. So ideally, when you have an incident, the root cause behind the incident should be fixed, so you will never have that class of incident anymore, right? That's the goal. Then in practice, like, things are slightly different, right? But the basically that's where you want to be, right? And then the primary goals of this analysis, right? And I want to emphasize this because some people I have seen in the past that tell, like, that takes a lot of time, right? Why would you do that if you already fix the service, right? Is to learn and to build institutional knowledge within your team of how to do things. So these things, these issues, these outages, these root cause never happen anymore, right? And needs to be documented for creating a corpus of best practices, to understanding what is the risk that you have in your systems, right? So basically, you need to have things documented, like incidents, like problems, and so on, right? And then make sure that you analyze the root cause, not the symptoms. Well, the symptoms, they need to be there because it's like informative, right? But you need to go to the root cause, right? And sometimes it's very hard to go to the root cause. There is this framework, the 5 whys, why, and then why, and then why, and then why, that typically takes you there, right? But it's usually the good postmortem takes a good chunk of time, right? One needs to blameless, right? You don't want to blame people for problems that are an issue of the system, right? So if someone could release a binary with a bug or a malformed CL or a dependency that should have not been there, is because the system allow them to do that, right? So that's the major problem, right? And then this one, the review. The review is what I wanted to cover, right? Because the review is where the learning happens, right? So the postmortem authors are typically the persons that are responding to the outage. They know already, right? They only then know. So the review is when, like, this is shown to the whole team of the whole company, right? And it is when everyone learns that your platform, your things, they have some shortcomings that we need to improve and we need to make better. This is when we move, for example, we decide to move out of global services, or we decided to, like, change some of the functionality in Borg, or whatever is the thing of the day, right? And this is testing. I think testing, you are all software engineers, so you know, like, the difference between this unit test, integration test, system tests. So do test, but the one word of advice is, like, a test is not a panacea, in the sense of, like, many people are obsessed about the coverage of unit test. Like, every single line of code of your project needs to have a unit test corresponding to that. That's great, right? But it's insufficient, right? So there are times where you might have less coverage of unit testing in your code, right? But if you have a system test, because what you are doing is integrating multiple components, right? It's going to have much more impact than covering your code, right? This is particularly sensible in things like if we go back to services that they have AI models and ML and all that stuff, right? System tests, they become really important because you might have coverage in all the code that you are doing to call an API, right? But we are moving quite some functionality to the prompts of LLMs these days, for example, and other systems in the near future, right? Because if you're in the past, you could do your graph analysis in code. There, having unit testing might help. If what you are doing is just crafting a prompt to pass to the Gemini API or GPT or whatever, right? Then is the model the one that is going to do all the things that you used to do in code in the past, right? For certain use cases, right? So having system tests where you prompt it with different examples, you retrieve the response, you monitor the quality of that, you make sure that the API is called correctly, and all that stuff will have quite a lot of impact, more than doing coverage on your framework that is just like sending text and retrieving text from an endpoint, right? So be careful on on that part. So, like, look for the complexity, right, and test that. And I'm gonna leave it here. So all of this, I think you can just read it to yourself. I don't think there is a whole lot of insight that I'm gonna give you in the, like, integration test. This is mostly the definition of it. What I think is gonna be interesting is if you ask questions now, or we have a discussion in the last 7 minutes that we have. I'm sure you might not have got or understood everything that I said. So, any question, complaints, or throw stones, not very hard.
Well, first of all, Ramon, thank you very much for this very, very exciting lecture and providing all those in-depth details about your work and your experience. It certainly helps us to set this class apart from other big data courses, because I talked a bit about ML ops a few weeks ago, but since now you talked about production in detail and site reliability engineering, I think this really helps us to contrast this to what we did. If there are any questions, everyone, now it's the floor is yours.
While you think about it, I'm going to send you my email, slides, material. So if you are not comfortable asking right now, feel free later as well.
We will anyway have the recording and put it live, and then because we have more students taking this course than those 30 who attended now the live session, so some will be watching the recording and may get back to you then after this. But there's a question now.
So, besides Systemantics, what are other resources you recommend to someone interested in SREs? Okay, Systemantics is a great book. Like, it's just, yeah, that one. It's, I think it analyzes systems in general, right? So I think it has memes and it's great. The other resources I recommend you is doing the following. There is the SRE book and so on, so you can just gloss over it to get the practice right and the details right. I would recommend you to put something in production, right? There is some GCP has free credits, for example, like if you're doing some of your assignments or your practice or your labs into like the course that you're studying, right? Go try to put it in production. Right, you are going to discover the cutting edge of things, like how ugly APIs are sometimes, how things are not as you wanted, like how your machine has some assumptions that production does not, right? All that stuff. So it's not going to take you like a whole lot of time, but you will discover where the pitfalls lie. You are muted, I think, Patrick.
Yeah, I guess they'll have more questions and then get back to you by email. And as I said, more will be watching this recording in the coming days.
Yeah, good.
Good. Thank you very much again. I'll stop the recording here.